So our quiz number 8 is going to cover topic 6.4, which is our advanced factoring, all the way up through inverse functions, which is 7.4. So the first section of the quiz is going to ask you to factor. So you can use your factoring flowchart for some inspiration. And the first step is to look for common terms. And I noticed 9 and 100, there are no common terms here. So the next thing I have to look for is the fact that it's two terms. It's probably one of my special patterns. These are both perfect squares. So the way I factor perfect squares is I take the square root of each term, so 3x and 10, and then one of the signs is going to be a positive and one of the signs will be a negative, kind of like the conjugates, because that's what makes the outer inner part of FOILing cancel out. Okay, number 2, there's a common factor of 4. Because we're just factoring an expression, I can't divide by the 4, it does have to stay out in front, leaving us with, let's see, 16. And then my remaining trinomial can factor further. So multiplies to negative 16, there's a few options, but I think if we do x minus 8 and x plus 2, that will add up to the negative 6 in the middle that I'm looking for. So this answer is my final answer. If you'd never factored out that common 4, you're not going to get the question correct. The next problem is two terms, so it's a special pattern. There's no common terms, but I notice they are both cubic numbers, which means it's going to factor as the sum of cubes. So remember the pattern is a plus b, and then a squared minus ab plus b squared. So I like to identify who a is and who b is. So the a for my problem is x, and the b for my problem is the cube root of 27, which is a 3. So filling into the pattern, I have x plus 3, x squared, minus 3x, and then 3 squared is plus 9. I like that pattern because it never factors further, so once you get the pattern filled in, you're done. The next question, there are no common terms, but you should notice it's two terms, which means it's a special pattern. We have a perfect square minus another perfect square, so it's very similar to number 1. If I square rooted x squared, I get x and x. And if I square root 64y squared, I get 8y and 8y. And then the pattern says one's a plus and one's a minus. Nothing factors further. You do want to double check on these patterns. Sometimes the remaining difference problem will still be squares minus squares. Not in this case, but just watch out for that on your quiz. Number 5, there's no common factor, but is a basic trinomial, so I'm going to try factoring it like a reverse FOIL problem. So to get an x to the 4th, I know I'm going to use x squared and x squared. Multiplies to negative 56 and adds up to 1 would be a positive 8 and a negative 7. Now this pattern in particular, oftentimes this subtraction term will factor again, not in this case because 7 is not a perfect square. So that is the final answer. And then in number 6, there's 4 terms, so I'm going to factor by grouping. I'm going to group the first 2 and the last 2. In my first group, there's a common factor of 3x squared, and when I factor him out, I'm left with x minus 5. And then in the second group, I'm going to factor out a negative 4, so that way I can have a lead term that's positive, and it's also going to leave me with an x minus 5. The reason they have to match is because now you're going to factor out the common x minus 5 in front of the entire problem, and when you take out the x minus 5, you're left with a 3x squared minus a 4. And then again, watch out for this term to factor for a second layer. This case it does not factor further, but for instance if it was a 9x squared minus 4, it would definitely factor further because it'd be the difference of two squares. Okay, number 7, they want us to find the inverse. First of all, just remember f of x is really just a y. Our first step in finding inverses is to switch the x and y, so it's going to say x equals 3y plus 5 over 4. And I need to eventually isolate the y, so we're going to cross multiply like a proportion. If 4x equals 3y plus 5, I'm then going to subtract my 5, and then a final step is divide everybody by a 3. And I'm going to divide them individually as separate fractions. So I end up with y equals 4/3 x minus 5/3. Now proper notation says instead of saying y equals, I should say function's inverse, or f to the negative 1 of x equals 4/3 x minus 5/3. And that's the answer I'll be looking for. Number 8, draw an example of a graph whose inverse is not a function. So if the inverse is not a function, and I am going to talk about his original function or possible function, this has to do with the horizontal line test. So I have to give an example of something that fails, in this case, the horizontal line test, because they want something whose inverse is not a function. So just a nice standard parabola will fail the horizontal line test, because if you drew a horizontal line in over there, it would touch the graph twice. Write an equation of a circle in standard form by completing the square twice. So these are review questions. I notice there's only one x term in the problem, so I don't have to complete the square on the x's, but with my y's, half of 12 is 6, 6 squared is 36. And then we're going to add 36 to both sides of the equation. Now you remember to, whoops, rewrite this perfect trinomial as the square of a binomial. So y and then half of b is plus 6 squared. Negative 32 plus 36 is 4. So I can identify my center as being at 0, and then negative 6 for the k, and the radius is the square root of 4, which is a 2. Okay, some more review. Simplifying. We are subtracting our like terms here. Just be careful, because squared should only go as squared, and I notice there's only one cubic term in the problem. So I'm going to start with a negative 5x to the third power, negative 6x squared minus a negative 8x squared. Be careful, that becomes negative 6 plus 8. Again, type on your calculator if you're unsure of it, but plus 2x squared. And then linear term 7x, there's no other linear term, so plus 7x. And then we've got a negative 11 minus another 11, so negative 11 minus 11 is negative 22. And next problem is deceptive because it looks very easy, and it's not that bad, but it is time consuming. We're going to expand this, realizing that he has 3 of these guys multiplied together. So you are going to multiply the last 2 together first, and when you FOIL that out, you get x squared negative 4x plus another negative 4x is negative 8x plus 16. And now we're going to distribute the x into everybody. And you get x to the third minus 8x squared plus 16x. And we're going to do the same thing with the careful negative 4. Woo! So let's see, negative 4x squared, I'm going to line them up, plus 32x. And then minus 64. So we end up with x to the third minus 12x squared plus 48x minus 64. And that's your final answer. Number 12. Neighborhood kids are going to build a tree house, and they're going to have a bake sale to fund it. And this time I give you the revenue function is 10x. Suppose the function for the cost is 4.5x minus or plus 15. First of all, they want to know what the pies are selling for. So that has to do with revenue. Apparently we're selling the pies for $10 a piece. And then the profit function, remember, is when you take your revenue function and you subtract off your cost function. So for us, revenue is 10x, and when we subtract the cost function, which is 4.5x plus 15, I just have to remember to distribute the subtraction sign to everybody in the cost, including the 15. So when I combine my like terms, let's see, that ends up being 5.5x minus 15. And I should have started this with p of x equals, sorry. That's an equals. And I'll find the profit of 50 pies. We're going to evaluate that new profit function at 50. And I think I already did that, and I got $260. Okay, we have function f and function g. And we're going to do various operations on that function, and we're going to determine if there's any domain restrictions. So number 13 says f plus g. I know the notation is weird, but that's all they want. So if I add x squared minus 1 plus x plus 3, the only thing I can combine are the constants, and I end up with that function. And since that's a quadratic polynomial, the domain is negative infinity to infinity, or all reals. 14 is f times g, so we are going to have a bit of a FOIL problem we have to work out here. because it's a binomial times a binomial. So we have x to the third plus 3x squared minus x, and then a minus 3. The good news about that FOIL problem is there's no more simplifying I can do. And because it's a cubic polynomial, his domain is all reals again, because there are no restrictions. This is composition f of g of 9. You could rewrite it like this if you prefer this notation, which I do. So I'm going to start on the inside and find g of 9. So evaluating g at 9, you get 9 plus 3, which is 12. So that means instead of evaluating function f at a number that was 9, now I'm going to evaluate function f at 12. So let's see, 12 squared minus 1 is 144 minus 1, or 143. And that final number we get is the final answer. And then number 16, there's no domain for the composition of functions at a number because you don't have a function anymore. Number 16, f divided by g would be f in the numerator and g in the denominator. And the only thing we have to talk about for domain is the fact that the denominator cannot equal 0. So the x value cannot be a negative 3. So that is my domain restriction, and this is my function. Okay, the next example, here's my new function for p and for q. They want p times q evaluated at 7. So we're going to evaluate p at 7, but also q at 7, and when we get our two answers, we're going to multiply them together and find the product. So p at 7 is 2 times 7 plus 3, which is 14 plus 3, which is absolute value, that is 17. And then q of 7 is 4 minus 2 times 7, or let's see, negative 10. And if I multiply 17 times negative 10, I get a negative 170. Now 18, be careful about the notation. This is the composition symbol, so it's q of p of negative 2. So I start on the inside and find p of negative 2, which is 2 times negative 2, which is negative 4, plus 3 is negative 1, but it's the absolute value of negative 1, so that's a 1. And then I'm going to go back and say evaluate q at that new number 1, which is 4 minus 2 times 1, or 2. I know the composition notation and the operation notation is a little strange. Number 19, this is a quadratic polynomial that's upside down, shifted up 5, so his vertex up here at 5. And you could use your calculator if you weren't exactly sure what that looked like, but I know with any polynomial the domain is negative infinity to infinity, because that's how far to the left and to the right. Now I did a really cruddy job of graphing this, sorry. The range, remember, is low to high, always low to high, so it goes down forever, that'd be negative infinity, and then it does reach a maximum value here, a y value of 5. And then end behavior always starts the same way. I know that the first end behavior I want to talk about is what happens when you go to the left, and the other end behavior is what happens when you go to the right. So when I look at my function, as I travel to the left, I see it's going down, and as I travel to the right, I see it's also going down. And I think that's the end of it. So that'll be your quiz for quiz 8.